All right, hello and welcome back. In today's lesson, we're going to be getting into Venn diagrams, and this will also be an introduction to simple probability as well. In Venn diagrams, there's kind of two big types. The first type is a two-circle Venn diagram, and the second type is a three-circle Venn diagram. And we'll mostly be focusing on the two-circle Venn diagram because all the fundamentals that we learn for this first type is going to apply to this one as well. So everything we learn here is going to apply to three-circle as well. Let's do it that way. All right, so with that being said, let's establish some basics for our two-circle Venn diagram. We can kind of see what our basic shape looks like here. And so we just need to put some info in and kind of label some big ideas. Very first thing to notice is that our Venn diagram has this outer box. And this outer box, sample space, we don't really need to worry about that vocabulary too much. We'll kind of get into it later. But just think U is all the possible outcomes. So that's what we want to keep in mind. Inside of our Venn diagram, we see two circles, and these two circles represent two events or two things that could happen. Most times you'll see these labeled as A and B. And as we get into questions, we'll see that these events could be just about anything that we want to work with. So this could be, again, the chance of rain and the chance of thunder. Two things that could happen separately or together. They could be representative of a student population, so it could be looking at students who study maybe math and history. And we could see again, who studies just history, who studies just math, who studies both of those subjects, or neither of those subjects. But as usual with math, we'll try to keep them labeled simply, so we'll say that our first is A, and our second is B. And so the very first thing that we want to talk about is our notation. And the notation that we use for probability is capital P of A. So this is a function. And we're saying that the probability of A occurring can be represented by some probability that goes from 0 to 1. So either there's a 0% chance of something happening or a 100% chance of it happening. We can never have more than that, and we can never have less than that. And similarly, we could say P of B represents the probability of event B occurring. So those are really simple, pretty straightforward. If we wanted to, in our diagram, we could label those with the probabilities of them happening. For instance, we could say that there's a 1 in 4 chance that A happens, or a 3 in 4 chance that B happens. And it would look like that. The next thing we would take a look at is what's called a complement probability. And complement probability is the chance of something not happening. And let's change that into some text. Maybe, yeah, let's change that into text. I feel like the pen's a little bit too thick. There should be a way to thin that out. Let's see. Oh, there we go. Okay. Oh, perfect. Okay, so let's fill this in as well. Probability B is the probability of event B occurring. Complement probability is the complement, so it's what is the pairing to what doesn't happen. So what we can say is that if probability of A is given like this, the complement of A is not A, or A not happening. And so in math notation, we write that as the probability of A not, like that. And similarly for B, we could say the probability of B is not B, or B not. And the notation for that is exactly the same. So it's probability of B not, like that. In our diagram, if we say that the probability of B occurring is inside of the circle, as we can probably guess, the probability of B not occurring is going to be everything outside of the circle of B. So we're going to get to our very first diagram of this lesson, and that's going to be to illustrate what that looks like within the Venn diagram. So we copy this down, and we're trying to highlight what probability of B not looks like. We can say the probability of B not, and we're going to need our highlighter quite a bit tonight, is everything outside of B. So we're basically taking this diagram and we're shading in everything that is outside of B. So that's going to be all of A except for that part where A and B overlap. All right, I think that's pretty good. So that's our probability of B naught. And what we can see from there is that the probability of B and the probability of B naught, when added together, is always, always, always equal to 1. And that's true for any complement probability. They always sum up to 1 because either something happens or it doesn't happen. And that gives us our entire sample space. So that's the very first topic. We call this complement probability. Pretty simple, pretty straightforward. Not too much to talk about there. The next thing that we're going to talk about is our intersection. And we're going to need another copy of that. So let's go down here, give ourselves a title. So intersection is exactly what it sounds like. A good way to think about intersection is that it's the place where our two things overlap. Or we can also think of this as our or statement. So you'll see why both of those are important just in a little bit, but for now we'll put this at the top. I'm going to say place where areas overlap. And this is also going to be our or statement. And there's also an English kind of translation of this. And our English translation says that we're looking for the place in our diagram where A and B, oh, I'm sorry, this is not supposed to be or, this should be and. And so our English statement is the place in our diagram where events A and B happen together. So that's kind of what we're looking for. And that's going to hold true not just for Venn diagrams, but for tree diagrams. We're going to see that for continuous random variables, discrete random variables. So this English kind of translation, we're going to see this over and over and over again. It's a really good one to know. All right, so let's take a look at what our diagram actually looks like for an intersection. There we go. So this is our diagram. We have quite a few different places where we can see our intersections show up. And we'll talk about the one that we kind of see first, and probably have learned first, maybe back in elementary school. If we're thinking about the probability of A and B happening together, we can write this with this symbol. It kind of looks like an upside down U, and that represents our intersection. So this is our intersection symbol. There we go. So that's our intersection symbol. And just like we mentioned, this is an AND statement. So if we say the probability of A intersection B, we're trying to find the place in our diagram where events A and B occur together. And that's probably pretty obvious to see where that happens, but we're going to use our method that we'll use for the intersections after this as well. We want to find first the part of the diagram that represents A, and we want to highlight that entire area. And then we want to do the same thing for B. And this brings us to what we talked about up above, where we see that these two overlap in the middle. And that overlap space that's kind of a dark blue or a purple, that is our intersection. And so anytime we're looking for an intersection, if it's in Venn diagrams, if it's in tree diagrams, if we're seeing this in continuous or discrete random variables, we're always looking for the overlap to find our intersection. So this diagram we see here, this is showing our intersection for A and B. And so we can highlight that, and we can label our very first diagram as this middle portion of the diagram being A intersection B, like that. And so we're going to repeat this process for the other intersections that we can also see. I'll put this up there. Okay, so trying to rearrange things a little bit. Taking a look at our second case, and we've learned about, again, complement probability. So we're going to combine those together, our intersection and our complement probability. We want to find the probability of A naught intersection B. I would say pause the video and try to sort this one out yourself using the method that we saw before. We want to highlight our A naught area, we want to highlight our B area, and we want to find our intersection of those two, the overlap. So we're going to start with our first term, and our first letter is A naught. So A naught, again, is everything outside of our A circle. And our second event is B. So B is going to be everything inside of the B circle. And so what we can see here is that our overlap area is shown in kind of a brown color. And so we label this area here as our probability of A naught intersection B, like that. All right, so summarizing that all up, we can see that the intersection of A naught intersection B is going to be just this part of B that does not include the center part. And so we can repeat this process 2 more times and see all the possible cases of intersection. So let's grab these two diagrams, and we'll just move that over here. And we'll take that and delete that. And let's see, erase this and erase that. And then let's get everything centered as well, like there. And so, oh, we need to erase these as well, and that as well. So, as you might guess, our next two cases are the probability of A not intersection B not, and the probability of A intersection B not. Take a second, fill these in, and if you haven't already, what we can say is that for A intersection B naught, it's going to be this part of the A circle. And for this one up here, oh, we're missing a parentheses. We're going to be taking a look at everything that's outside of A and B. So we're everything outside of the two circles. And so those are the four cases that we can possibly have for intersection. All right, moving down, we take a look at our next topic, which is called union. Union starts with a U, and it's also represented by the shape, or, well, we shouldn't say shape, represented by the, what's the word I'm looking for, notation, a large U like that. And that should hopefully allow us to convert that into the correct LaTeX. Let's see if this will work. So that's the shape for union. It's a giant U. Pretty obvious, pretty easy to remember. And so our intersection is our other one. This one is known as our OR statement. And so let's once again go ahead and put in our definition. So for union, this is the place in the diagram where A or B occurs, or A and B occur together. As you can imagine, this is three separate cases we're talking about. So we're thinking about where does A happen, where does B happen, and where does A and B happen together. And so generally, our union probability is going to be larger than our intersection probability. Another way to think about this is we are looking for where one occurs, where the other occurs, or where both occur. And we have to do one extra step here, in that we have to make sure we're not double counting areas. And we'll talk a little bit about what that means here in a second. So in terms of the diagram, we are adding all the areas together and subtracting any areas that are double counted. I think we can probably take this down a couple of font sizes. So up here, again, we're seeing that our intersection is our AND statement. Down here, this is going to be our OR statement. So what does that look like? Well, the very first thing we need is a diagram for us to use. And let's grab one of those to put in. All right, so for our union, again, this is going to be our OR statement. If our two circles are labeled as A and B, and we ask the question, what is the probability of A union B? When we convert that into English, what we're saying is, where does A happen, or B happen, or A and B happen together? And that's hopefully pretty obvious. We can see that A is everything here in our A circle, once again. And if we look for where B happens, it's going to be everything inside of the B circle, once again. And if we look for the place where A and B happen together, we can see that it's the inside space here again, the intersection. And so if we add all those together, we can see that we're double counting this inside area. And so this gives us our very first formula, and this is our intersection formula. Sorry, our union formula. So we say that the probability of A union B is equal to the probability of A happening or B happening. But again, if we add A and B together, we're double counting that center, so we need to subtract away the intersection of those two, which we can now write like that. So this is our formula to find the union of those two events happening. And just like we saw above, where intersection had 4 cases, we again have 4 cases for this here. So let's take a look at those 4 cases down below. So starting with our first one over here on the left, we're going to take our very first event, which is our A naught being here. A is everything outside of A. So once again, that's going to be everything outside of both circles plus part of B. And our second one is going to be the event B. And the event B, of course, is everything in here. And so what we can say is that for union, we're not looking for an overlap. We're looking for everything that's shaded in. And so what we can say is that our union here is the pink, it's the blue, and then we also have to subtract away anything that gets double counted, which we could see would be this part of the diagram. And from before, you might know that this is the probability of A naught intersection B, like that. So we can say here, the formula for the probability of A naught union B is going to be equal to the probability of A naught plus the probability of B minus the probability of A naught intersection B, like that. And if we combine all that together, we're going to see that we just get one single area. We can kind of see our final result there. That's the probability of A naught union B, where B is shown in blue. And so we can do the same thing for our last 2 examples. And for these, we'll jump right to the answer. We're looking for the area A, which is all of circle A. We're looking for B naught, which is everything outside of B. And so when we go to shade that in, that's everything except for that little part of B. So we're covering everything here except for that part of B, where that area would be the probability of A not intersection B. So it looks something like that. And then similarly, if we did our very last one over here, the probability of A naught union B naught, A naught is everything outside of here, outside of A, like that. The probability of B naught is everything outside of B. And when we add those together, that's everything inside of our diagram except for the intersection. So we get that. Now, this is not important, but what you might be thinking about is, well, based on this diagram, we kind of come up with a new formula. We can say that the probability of A naught union B naught is very clearly 1 minus the probability of A intersection B, like that. And using this type of thinking, we can kind of create an infinite number of equations about probability just by looking at the diagram. If you look at your formula sheet, you'll notice there's a certain set of formulas that you need to know, and those are the ones that we're going to focus on. But as we get into the advanced questions, we'll have to look at the diagram and come up with equations like these to help us solve. And we'll see that in the practice problem at the end of this lesson. So what we see here is our 4 possible cases for union. We have the probability of A union B shown here, which is both circles. And then we have the probability of A not union B, A union B not, and finally the union of A not union B not. All right, up next, we're going to take a look at our conditional probability. So conditional probability is really challenging for a lot of students at first, but it's actually really simple. It's just a matter of changing our sample space from the entire rectangle U to just what the given condition is. So conditional probability. Conditional probability is always given in 2 parts. And so we say this in English as the probability of event A given that B has occurred. So what this kind of means is that there's some condition that's already been met. And because that condition has been met, it actually changes the probability of something happening. So for instance, if we say we're looking at a diagram, and in this diagram, there again is the simple example of rain and thunderstorms. What we can say is that if we know that it's raining already, there's an increased likelihood that it's also thunderstorming. And so this kind of brings us into this idea of conditional probability. If we're given some prior information, it changes the chance of another event happening, if those events are dependent or independent, which we'll talk about pretty soon. So again, what we can say here is for conditional probability, we're taking a look at maybe just 2 things to start. We could have more than 2 events. And in this case, it could be maybe rain and thunderstorms. And let's leave that off. And we should introduce our notation. So conditional probability can be written in this way: the probability of A, and then we use this vertical bar, given B. And let's change that into the tech. So this is our notation for conditional probability, the probability of A given B. And the way that we find it in the diagram, like we mentioned up above, is to find our given condition and set that as our new sample space. So again, usually we're considering the entire sample space, which is the entire box. But if we have a given condition, that means our space that we're considering is just going to be the given condition space. So let's take a look at the 4 possibilities that we can see here. Starting with this one, we say that our given condition is B. And so we're only looking at the part of the diagram where B happens. And then we're saying, well, what's the probability that A happens given that we're only looking at B? Well, inside of that B circle, there's only one place where A occurs, and that's right there in the overlap. And so what we're saying to find this probability of A given B is that instead of looking at the entire space, we're looking at just the part of the diagram. Again, that's the given condition. And then we're looking at the outcomes that meet the condition of A occurring, which happens to be this intersection area. So the probability of A given B is given by this formula here. And visually in the diagram, it means that we're looking for, again, the part of the diagram where the given condition is met, which is B, and then we're putting that on the bottom, or the denominator. Oops, that's the wrong color. So that's our denominator, our whole sample space we're considering. In the top, we're taking a look at the place inside of our given condition where A happens, which happens to be the intersection, like that. And so if we take the probability that's there, divided by the probability that's in the green area, that will give us the probability of A given B. We're not going to put any numbers to this until we get into the homework or the practice problem. Right now we're just really looking at the intuition, we're looking at the diagrams to get a feel of what it means. Just like before, we're going to have 3 more cases. So our first case is going to be the probability, well, our second case, probability of A not given B. And then our third case is the probability of A given B not. And then finally, the probability of A not given B not, like that. Okay, so with our 3 diagrams in place, we're going to go through the first one together, and just like before the last 2, we'll do a little bit more quickly. Take a second, pause the video if you need to. We're going to try and fill in what our conditional probability looks like for the probability of A not given B. As before, we're going to take our given condition, which is B occurring, which is right here. And then we're going to take our other condition, our event A not happening, and we're saying where inside of this sample space, now that's just limited to the green circle, where does A not happen? And we can say, well, it occurs in this portion of B. So in order to find the probability, if we had numbers in these diagrams, we take whatever number is in our red part and we divide it by the number that's for our green part. So we take our red and we divide by our green. And that would be our probability of A not given B. All right, over here, same thing. We're going to start with our given condition, B not. This time B not is all out here. And the condition we're looking for is when does A occur given B not? So that should also include that. So we can see for this one, A occurs just in this portion of the green area. So again, if our diagram had numbers, we take the numbers for the green area, that would go on the bottom. And then our red, pink area, that's going to be our numerator, and that would give us our total probability. All right, one more. And we have the probability of A not given B. And so again, our B not is everything outside of B. And now we're looking for A not. So where does our A not lie? Well, A not is everything outside of A, which does include this, but again, we're only looking at the green sample space, so we're looking at everything out here in our diagram, like that. Let's redo that. So let's reset that to there. That looks a little bit better, yeah. All right, as you might imagine, there's actually 4 more cases for this one. So there's also the case of the probability of B given A not. There's the probability of B not given A not. There's the probability of B given A. And finally, the probability of B not given A. And if you want to, you can take some time to draw diagrams for each of those, but you can kind of get the idea. For conditional probability, we're changing the sample space that we're looking at, and then we're looking for the area inside of that new sample space in order to calculate our conditional probability. All right, that brings us to independence as our next topic. Independence, let's see, did we do the formula for conditional probability? Yes, we did. Okay, cool. Independence is asking the question, are these two things dependent on each other? So if event A happens, is it more likely that the other event will happen or less likely that the other event will happen? So that's kind of the guiding question. If event A happens, does it cause the other event B to happen more or less often or the same? Within our Venn diagram, this is actually a pretty hard question to answer because the Venn diagram doesn't visually really show us what this means. And so what I would say here is that we should wait until we look at tree diagrams in the next video to really dive a little more deeply into this question. But the formula is pretty useful here. So independence, we should say here, Venn diagram is not very helpful in seeing this property, in seeing, let's say, independence. And we can also say that tree diagrams are much more useful here. So we'll kind of set this one aside. The reason why Venn diagrams are not great for seeing this is because Venn diagrams are not to scale. So that's kind of why this is so unhelpful. Let's see if we can grab a diagram. Okay, so we have a Venn diagram here. We're mentioning that it's not very helpful to be able to see independence. One of the big reasons that we can't see independence just from looking at the diagram is that a Venn diagram is not to scale. That's a really important aspect of Venn diagrams. So we kind of give it this big sticker, not to scale, not very useful. We will come back to this topic again for tree diagrams. Anyway, we can say that our Venn diagrams are not to scale. So visually, there's not really much we can get intuitively by looking at a diagram. But we'll mention here real quick the formula for independence. So if two events are independent, we can say that the probability of A times the probability of B is equal to the probability of A intersection B. So this is kind of like our test number 1 for independence. There's a second test using conditional probability. And we can say for our second test, let's try that again, that two conditions have to be met. And that condition is that the probability of A is equal to the probability of A given B. So basically we're saying the probability that A happens is the same even when we know that B has occurred. So knowing that B has occurred, it doesn't change the probability that A has happened, which is the definition of independence. It's saying that these two events don't cause the other one to be more or likely, less likely to happen. And so we say that one has to be true, and then also the probability of B has to be equal to the probability of B given A. Again, we know that A has occurred. It doesn't change the probability that B occurs, more or less likely. So for now, we're just going to give these formulas. Venn diagram, not super helpful for seeing what that means. And we'll get to the tree diagram and the intuitive visual understanding what that means in the next video. All right, we have one more thing. That's our mutually exclusive events. And mutually exclusive events are something that is very easy to spot in a Venn diagram. So mutually exclusive events means that events A and B cannot occur together. Pretty easy, right? You might even have a guess of what that will look like. If events A and B cannot occur together, one of the concepts that we learned earlier in this lesson has to be 0, right? So we know that our AND statement, and that is our intersection. So we're saying that the probability of A intersection B is 0. They can't occur together. And so visually, that's really easy to spot in a Venn diagram because these two circles, let's copy this, are going to have 0 overlap. So this is a case where we have mutually exclusive events. A and B cannot occur together because their intersection is 0. We're going to move into the practice question, and let's get that onto a new page. This is practice problem number 1. We are given two events, A and B. The probability of event A happening is 5/16. The probability of B happening is 1/8. And we're given that the probability of A happening when B occurs is 1/2. Based on this information, this question is not asking for it. Do we think that events A and B are dependent or independent? That's correct. So we can see that the probability of A happening changed when we know that B has already occurred. And so because those two probabilities are different, we can say A and B are dependent. And not necessary for this question, but just something good to practice. We'll see more of that again in the next video. So let's start with part A. What's the probability that both events will happen? Very first thing we can do is we can create ourselves a little Venn diagram. So we have a diagram here. And in this diagram, we can go ahead and take our information and put it in. So event A, the whole circle, is 5/16. For B, it's 1/8. And then the probability of A given B is 1/2, which is not too helpful. As we saw before, if we try to put that into our diagram, we're saying that B happening is all of this, and A happening in that circle is going to be that part. So we're saying basically, let's try a different color. Let's say yellow. Oh, that doesn't really work that well either. Maybe blue. There we go. So this purple area here divided by this pink area would give us the probability of A given B. And we can also say from our formula that we saw before that the probability of A given B is equal to the probability of A intersection B over the probability of B, like that. So we know our probability of B, we don't know our intersection, but we do know our given probability. So if we take that formula and we plug all of our values in, we can solve for this first part of the question. So let's move that up there, and let's move this over here. So we'll start over here. We'll say the probability of A given B is 1/2. That's equal to the intersection, which we don't know, but we're trying to find that out. And then the probability of B happening is 1/8. So just by doing a little algebra, taking our 1/8 and moving it over, we get 1/2 times 1/8 is equal to the probability of A intersection B. And finally, we can say the probability of A intersection B is equal to 1/16, which we can then go ahead and put into our diagram, like that. A little rearranging, we're going to now move to part B. Part B says, what's the probability that only one of the events will happen? So that's asking us for the probability that B happens without A happening, or A happens without B happening. If we translate that into English, from English into algebra, we can say that the probability of A intersection B naught would be the place where A happens and B does not happen. And if you need to, you can look back at our notes. or you can look at the diagram and you can confirm that, again, this is the case where only A occurs, like that. The second probability that we're looking for is when only B occurs, and so that would be the probability of A not intersection B. So we could say that this one is the probability, again, of only B happening. And so we could say, well, how could we find that probability? First thing we can do is we can go into our diagram and maybe, well, we can label it. So we'll say the probability of A intersection B naught is this one. Again, we learned that one before up in the intersection section. And then similarly, this area over here is the probability of A not intersection B, like that. So if we can find the probability in those two areas, then we're done. Well, something you might have noticed is that in this diagram, these two circles in total, so both circles together, that's the probability of A union B. So if we could just find that probability and subtract away that intersection, that would give us the two probabilities that we want. So if we want to find these two here and here, by looking at our diagram, we come up with our own custom formula. We talked about this before, and this formula states that that would be equal to the probability of A union B, both circles added together, minus the probability of A intersection B. So the very first thing we need to find for this one is we need to find the probability of A union B. If we go back to what we know that's the probability of A, which is 5/16, plus the probability of B, which is 1/8, minus the overlap, because we don't want to double count that, so A intersection B. And then we're subtracting that intersection again, like that. But that will happen in the next step. So for now, we're just going to find our probability of A union B. That's 5/16 plus 1/8, or 2/16. And then we subtract away the intersection, which is 1/16. We add that together, we get 5 plus 2 is 7, 7 minus 1 is 6, and we get 6/16, or 3/8. So 3/8 is the total probability, again, of both circles. So that's all of this stuff. And so to get our final result, we just need to subtract 1/16 one more time. So we're saying the probability, again, of only A and then only B is equal to the probability of A union B, which we now know is 3/8. And we subtract away the intersection, which is 1/16. And so if we get a common denominator for that, we multiply the top and bottom by 2, we get 6/16 minus 1/16, and that gives us 5/16, like that. And that's our part B. Cleaning that up a little bit. Now moving to our very last part, we're looking at part C. We want to see what's the probability that neither of these events will occur. Take a second to think about which probability that represents, and hopefully what we're thinking when we convert that into notation is the probability that A does not occur, and at the same time, B does not occur. So we're trying to find the probability of A naught intersection B naught. And again, if you remember from before what part of the diagram that is, we are taking a look at the outside area. So the probability of A naught intersection B naught is everything outside of here. And we can very clearly see that that area is everything inside of our sample space, which totals 1. subtracting away everything that's inside of the two circles. So again, we mentioned this formula before. It just so happens that this is equal to 1 minus the probability of A union B. So we calculated A union B down here, and we said A union B is 3/8. So to solve this one is really quick. We just say 1 minus 3/8. And doing that, we get 8/8 minus 3/8 is equal to 5/8. And that is our final answer for part C. And that brings us to the end of this question. So that's our part C. Like that. All right, so let's just do a quick recap of everything that we talked about as usual. If we go all the way up to the very top, we are taking a look at Venn diagrams today. There are two types that you'll see in IB Math, the 2-circle and the 3-circle. Today we're just looking at the 2-circle case because, again, everything we learned here will apply to the 3-circle case. The 3-circle case type questions are much, much simpler, and you won't have to look at things like conditional probability and independence. Once we get into those questions, you'll see that those are a lot simpler. Down here, we start with our very first idea, which is our sample space. Our sample space is represented by the rectangular border. That's all the possible outcomes. The sample space must always add up to 1. We talked about our notation for probability. So we say P of A to represent the probability of event A occurring. And we have the complement of that, which is represented by an apostrophe. And we say the probability of A, apostrophe, the probability of A not or not A. Either one is okay to pronounce. Coming further down, we see a demonstration of what that looks like. This is B and then B not in red. That brings us to our first idea, which is intersection. Intersection tells us where two events that are given, where they occur together. And so there's 4 total ways we can have intersections in a 2-circle Venn diagram, and those 4 are shown. Our intersection is our AND statement. So A and B occur together. That's what we're looking for. Not only in Venn diagrams, but tree diagrams. We're going to see that in continuous random variables and also for discrete random variables. Union is our OR statement. It's represented by this large U. And we're saying the first event happens, the second event happens, or the 2 events happen together. So we're looking at 3 different places in our diagram, and this is our very first case and our other 3 cases. That brings us to conditional probability. Conditional probability changes the sample space that we're looking at from the entire rectangle to just the given condition. So if it's the probability of A given B, the given B is just that circle, and we're only looking within that circle to calculate our probabilities. And these are the 4 conditions, and then there's actually another 4 in total. So we have 8 total conditions for conditional probability within the Venn diagrams. Independence, as we talked about, is not very easy to see with a Venn diagram, but we gave ourselves 2 tests we can do to see if events are independent or dependent. And we're going to talk about this more later when we get into tree diagrams. And then finally down here we have mutually exclusive events. And for mutually exclusive events, they are events that cannot occur together. And so we see that their overlap is actually going to be 0. These 2 circles are completely separate. All right, and then we jumped into our practice problem number 1. And we saw how having knowledge of the Venn diagram, knowing how to shade the areas, find the overlaps, and the intersections can help us solve, come up with custom formulas when it's a little bit harder. And if we spot something that we've seen before, we can reuse that result and get an answer a little bit more quickly. All right, that's all for Venn diagrams. As we mentioned before, there is a handout sheet with all the formulas in one place. And these notes will also be available, as always, down in the description below. All right, I will see you all in the next one.